All right, chemists, this is the first lesson in our equilibrium unit. Equilibrium refers to reversible processes. Many reactions and physical changes, of course, are reversible. That's what the equilibrium unit is all about, the reversibility of processes. We reach what's called a dynamic equilibrium when the concentrations of species are constant. So not changing over time. But when the rates of the forward and reverse processes are equal. I can't stress this enough. People often misconstrue these two things. Concentrations are constant, but rates are equal. Concentrations are constant, but rates are equal. Concentrations starts with con. Constant starts with con, so you can remember that pretty easily. And we can apply the reversibility to all of the reactions we've talked about, frankly. This is something we can actually always consider. But today we're going to look at fairly irreversible processes, and we'll see how we can manipulate them using various techniques in the laboratory to drive a reaction more in one direction than another. Here's a very famous reaction, the Haber synthesis of ammonia, done by Fritz Haber. This was huge in fixating nitrogen, useful for making fertilizers, and really transformed the agricultural industry quite a while ago. And it's just the combination of nitrogen and hydrogen to make ammonia. We write it with a pair of reversible arrows. Now, thinking back to our previous unit on kinetics, we can write a rate law for this reaction. And let's for a second just pretend that this is an elementary reaction and it's only going forward. Then we would write the rate as rate is equal to K times the concentration of each reactant, bracket N2, bracket H2 raised to their coefficient, so H2 cubed. I'm going to call this the rate of the forward reaction and the rate constant for the forward direction. And above that equilibrium arrow, I'm going to give it a little Kf, just meaning that's what's going on with the forward. There is also a reverse reaction, and it will have some other rate constant, K sub r, and it will therefore also have a different rate expression. Rate sub r, meaning reverse, is equal to K, but a different K value, K reverse, times the reactants with respect to that direction, which would be the ammonia. So times bracket ammonia, and then squared, because its coefficient is 2. Now, chemists have defined an expression, an equilibrium constant, which is the ratio of the rate constants. This is capital K. I'm going to say EQ, meaning equilibrium. And the ratio is the ratio of the forward rate constant divided by the reverse rate constant. So now, if we set those expressions equal to various things that are in terms of rate and then divided by these things, the K forward would be rate forward divided by these things, and the reverse rate constant would be the rate divided by the ammonia squared. But remember what we just said. At equilibrium, rates are equal. So those two things are equal to one another at a state of equilibrium. So the ratio of the rate constants actually becomes a ratio of concentrations. It will be whatever's on the product side, once you rearrange everything, the ammonia squared divided by the nitrogen times the hydrogen cubed. So anytime we look at a reversible reaction, we can write this as an expression. Now let's graph what this looks like. What do we mean rates are constant, or rates are equal and concentrations are constant? Well, let's say we start with some amount of hydrogen and then some arbitrary amount of nitrogen, and we're just monitoring this reaction. And then we're looking at how NH3 grows in, and we're going to start with none of it. Let me actually make these different colors. Let's keep the hydrogen blue. Let's, for fun, make the nitrogen red. And let's make the ammonia black. Now, as time goes on, we know from our kinetics unit that the concentration of hydrogen will decrease with time. This is not a first-order process. The nitrogen, likewise, will also decrease. It will decrease more slowly because it's not consumed at the same rate, but it'll have some different rate. It may end at a different amount. The ammonia, likewise, will increase as time goes on, and they'll just reach eventually some plateau. And it's this plateau point where everything no longer changes and you get to an equilibrium. The rates were different in the beginning because that's the slopes of the tangents. But here the rates are equal. I mean, they're all flat at this time. It looks like they're not even changing concentration versus time, but actually there is a dynamic equilibrium. There is a forward reaction and an equal reverse reaction. But what equilibrium looks like is when the concentrations of things no longer change with time. For every amount of ammonia that's being produced, there's amounts of hydrogen and nitrogen that are being consumed. So you have this what looks like a static system, but in fact it is dynamic. It is continuing to happen. Make a couple of notes for yourself. K only changes with temperature. And what's more, K only includes aqueous and gaseous species. We do not include pure liquids or pure solids in the expressions for the equilibrium constant. That has to do with the way that these are actually measures of what's called an activity of a substance, which is technically a unitless quantity. And for the activities of aqueous things, we divide it by a 1 molar, and for gaseous things, we divide it by a 1 atmosphere. So these are always in molarity, and these are always in atmospheres. You actually get a unitless equilibrium constant. That's how most textbooks treat this, so I'm going to follow suit with that. So let's practice just looking at a reaction and writing the expression. The expression for the equilibrium constant is simply everything you have on the right-hand side raised to its power of a coefficient divided by everything you have on the left-hand side raised to its coefficient as an exponent. So I'm going to draw a big fraction and write bracket NO2 to the 4th, bracket H2O to the 6th. On the left-hand side, I have bracket NH3 to the 4th, and then bracket O2 to the 7th. I included everything because they happen to all be gases. We don't usually express gases as molarities. We usually express them as pressures, and there's actually a different expression for pressure. We'll get to that in a moment, but you can actually interchange one and the other, and you'll see that shortly. I'd like you to just hit pause here and absorb that for a few seconds and see if you can come up with what the expression would look like in terms of concentrations for that last one there, the phosphorus pentachloride decomposition. Okay, let's see how you did. Well, I see a solid and a liquid, so I don't include those in my expression. I actually only include the gaseous Cl2, which I'm going to write as a molarity, and it's to the 1st power. Done. That's it. The rest of those have an activity of 1. So they're in the expression, but they're buried as a unitless quantity, and it just happens to be 1. The activity of a pure solid or a pure liquid is 1 for reasons that are beyond what we go through in this class. All right, we just said a moment ago that we sometimes have expressions with gases, and there is an expression that's in terms of pressure, and I'll show you what it is, what you do when you have pressure. So if I wanted to write the equilibrium constant for some generic reaction, A plus B goes to X plus Y, we can write an equilibrium constant in terms of concentrations, Kc, meaning in terms of concentration. So that's still what we've been doing. That is the products X times Y over the reactants A times B, all raised to their coefficients, little x, little y, little a, and little b. There's also an expression in terms of partial pressures. It's K sub P. That just means pressure. So we're not going to use molarities here. We're going to use partial pressures. So the partial pressure of X times the partial pressure of Y, all over the partial pressure of A times the partial pressure of Z, and everything raised to its exponent, xy, a, and b. And these things are not necessarily equal to each other, but they're related. They're related from our equation from last semester. PV equals nRT. That's true for bulk gases. It's also true for just any individual gas. If I want to talk about not the total pressure, but the partial pressure of, let's say, gas X, that's based on how many moles of gas, whatever X is, I have. Remember, the collection of gases is always at the same temperature, and all gases occupy the entire volume. So there's no such thing as a partial volume or a partial temperature for our purposes. They fill up the whole space, and they have some temperature. But a given amount of moles will have a given partial pressure. That means the partial pressure of X is equal to the moles of X times R times T divided by the total volume. What's moles over volume? That's molarity. So I can actually substitute in the partial pressure of X is really equal to the molarity of X times RT. And now that I've done that, I could do that for all of these partial pressures. So I'm going to use this and substitute it into all of these partial pressures and rearrange and write what Kp is now equal to. That means K in terms of pressure is a very big fraction. It's going to be the partial pressure of X, which is molarity of X RT, times partial pressure of Y, which is molarity of Y RT, but each of those is in its entirety raised to the exponents X and Y. And in the denominator, I have the same thing, molarity A RT, whole thing raised to A, and then molarity B RT, whole thing raised to B. And now I'm going to do some math tricks here, and we're going to factor out some stuff. I have a common base of RT in all of these terms raised to different exponents. So I'm going to factor that out and put it at the end, and what I'm left with is concentration X to the X, concentration Y to the Y, all over concentration A to the A, concentration B to the B, times the base RT to the, well, we have X and Y in the numerator and A and B in the denominator, so that's raised to the sum of X plus Y minus the sum of A plus B. And we actually go ahead and abbreviate that. That's just the molar coefficients of the products minus the molar coefficients of the reactants. So chemists call this delta N, meaning the reactants minus the product coefficients, just whatever they happen to be. And if I look at the left-hand side, what's this? That's just Kc. We defined it earlier. So I can reduce this down to Kp is equal to Kc times the quantity RT to the delta N. You might see that expression in your book or on reference tables, but that's where it comes from. The pressure equilibrium constant is equal to the concentration equilibrium constant times RT to the delta N. Now we have a couple of values of R, don't we? And you can always figure out which one you're using. If you ever have anything related to PV equals nRT, you know that R is the ideal gas constant 0.08206 in liter atmosphere per mole Kelvin. If it's stuff that's not related to PV equals nRT, then it's the other R value, 8.314 joule per mole Kelvin. We'll see that a lot more in the rest of the spring semester of this class. Okay, so that's just a quick derivation to put into your notes so you know how the different equilibrium constants are related. Let's wrap up with what happens when we change the way a reaction is written. I'm going to call this manipulating the equilibrium constant. Let's say I have this equilibrium forming ammonia, nitrogen and hydrogen makes ammonia, and I actually know what the values are at equilibrium. I want what the K value is numerically. So K is the concentration of our products squared F divided by our nitrogen times our hydrogen cubed. I'm not going to write out the expression. I'm just going to write out what the numerical values are. In the numerator, it looks like we have 0.031 squared. And in the denominator, I have the nitrogen value is 0.85, and the hydrogen value is 0.0031. But I cube that. And if I plugged it into a calculator and round 2 sig figs, I get 38,000. Pretty big K value. We'll talk about what that means at the end. What happens if I write this reaction differently? If you look at B is actually the same reaction, but it's reversed. This is just the reverse reaction, and it turns out that K actually depends on how the reaction is written. We'll learn in a later unit that it's based on a per mole property called the Gibbs free energy related to that. So it actually changes based on how you write a mole of reaction. And if you think about what would happen to the expression of K, just by flipping reactants and products, that means everything that was a product is now in the denominator, and everything that was a reactant is now in the numerator. So this becomes the reciprocal. So the equilibrium constant for this reaction is the numerical value we just found reciprocated, which is 2.6 times 10 to the negative 5. It's a very small number, and that means something about this direction of the reaction as opposed to this direction of the reaction. So knowing that, I'd like you to see if you can hit pause one more time and try to figure out what would be true about the third option. Look at how this reaction is written compared to the first two. What's that going to do to the numerical value of K based on what it does to the expression? Okay, let's see how you did. Well, this isn't reversed anymore. This is the same direction as what we saw in A, but all the coefficients are halved. Coefficients are halved. And when you change the coefficient for a K value, that changes the numerical value by changing the exponents. So here, Kc is going to be our original value, 38,000, but every single coefficient has been halved, which means every exponent is halved, which means this goes to the 1/2 power. So I take the square root of the K value, and I get 190. It seems a little bizarre because we just changed the coefficient ratio, but again, K is based on a property. It's very much related to a property we're going to get to later on, which is the Gibbs free energy, and that's actually related to how many moles of reaction we have for a certain substance. So this will make sense when we get to that later, but for now, just know that if you change the way K is written, it actually changes the expression and therefore the numerical value. Okay, lastly, what does the numerical value of K actually tell us? What does it mean when K is really big or when K is really small? We'd by default read reactions left to right, and a large K means that products are very favored at the equilibrium point. So this means that a very large K value for this reaction at whatever temperature it is mostly ammonia and not that much nitrogen and hydrogen, whatever the conditions of the reaction are. And then likewise, a very different reaction with a much smaller K value would be very reactant heavy at equilibrium. So a small K value means that reactants are favored, are dominant, I should really say, are more significantly present. That's what I mean by favored. An equilibrium mixture is always dynamically going back and forth between the reactants and the products, but you don't have equal amounts of things, you have constant amounts of things. So the magnitude of K is really informative in terms of what that reaction's doing at a state of equilibrium, which is where every reaction is trying to get to. There's one last thing we use, which is comparing the expression K with an identical expression, but not at equilibrium. This is called the reaction quotient, so we give it the letter Q. K is at equilibrium, but the same exact expression, the reaction quotient, is just not yet at equilibrium. call this the quotient. Same exact expression, but it tells us where we're headed compared to equilibrium. For example, if Q is equal to K under whatever conditions we are, well, that's a point of equilibrium. Nothing interesting there. We're already there. But what if we're at some point, the beginning of a reaction, and we just set it up and we want to compare where Q is relative to K? If Q is larger than K, that means there's too much reactant. That means we have, oh, wait, sorry, I got that backwards. If Q is greater than K, that actually means there's too much product. And therefore, the reaction is running in the reverse as it tends toward equilibrium. To reach equilibrium. You can actually remember this a little more easily if you simply write K first and compare it with K. If K is less than Q, you can think of this as a little arrow pointing to the left, and that reminds me the reaction is running in reverse. It's going backwards. We can actually use that trick for the last thing to write down for today. If Q is less than K, aka K is greater than Q, that trick we just used, use that greater than sign as an arrowhead. That means the reaction is running forward, and that's true. A K value that's greater than Q means there's too much reactant. The denominator is too heavy, and the reaction is running forward, meaning more so as it heads to equilibrium. So that's just an introduction to the quotient. We haven't even used it, but we will going forward into almost every unit remaining in this course. So that's just an introduction into the equilibrium constant, what it means, concentrations are constant, rates are equal, how it's related to pressure expressions, and then how it changes with the reaction, the way it's written, and comparing it with a state of non-equilibrium.